Hello, test subject. We have now released your grades. Cake and grief counseling is available in conclusion for your test. Despite our best efforts, you may have learned quicksort and sophisticated Fibonacci. We highly recommend that you not attempt any grok exercises. We have determined they are above your intelligence. I do not think I have ever met someone as bad at big O proofs as you are. You can try prove me wrong, but that would be a proof. Ha ha ha, that was a laugh.
So, of course, our special guest for this week is GLaDOS from the Portal series of video games. And while GLaDOS may take a slightly dim view of your intelligence, I personally am very well assured that all of you have what it takes to complete the class. So don't worry if your scores on the first mid-semester test were a little lower than you'd like. We now have a great opportunity for you to bump that back up with the project, which, remember, makes up a much larger component of your assessment and also gives you the ability to really show the skills that you've been developing throughout the semester. In the last lecture, we learnt about strings in C. Unfortunately, C has no strings, just like Pinocchio. But we did find a special C string type that we could import through a library that was just an array of characters. But with our array of characters, we still have to write algorithms that perform useful functions on them. Some of the functions were available for us in the C standard library through including string.h. We had string copy that we saw two different versions of, one using pointers and one using arrays. And today we're going to do pattern matching. This is to say, if you have a very large body of text, and somewhere in that large body of text you want to find something smaller, how do you go about finding that smaller substring within your larger string? It turns out that this is a pretty important problem. One instance where this might come into play is in bioinformatics.
These genes contain the instructions for making proteins. When a gene is switched on, an enzyme called RNA polymerase attaches to the start of the gene. It moves along the DNA, making a strand of messenger RNA out of free bases in the nucleus. The DNA code determines the order in which the free bases are added to the messenger RNA.
Now that you've had a very short introduction to genetics, who would have thought in Foundations of Algorithms you'd be learning some biology, you should be well equipped to deal with the presence of the genetic code inside your assignment. But in order to help motivate us a little more, so yeah, we've got this code, I knew that there was this thing called DNA, why are we going to look for specific sequences within it? There are all kinds of medical conditions that rely on abnormalities in the genetic code. One of these is HFE, hemochromatosis, which occurs when there's a mutation in a particular gene and causes excess iron deposition from the blood into various organs. This can cause all kinds of really unpleasant symptoms, but we do have a way to intervene and help patients if it's detected early. What you can do is you can intentionally remove some of the iron from someone's blood in order so that you don't get these buildup of deposits. But to detect it early, we have to find this particular mutation. This is the C282Y mutation. And our strategy for finding this mutation in a real person's DNA, we're going to cut up their DNA using biological pattern recognition. So there'll be some enzyme that we apply to a sample of their DNA. This is called restriction endonucleases. And we will cut up their DNA into little fragments, amplify those fragments using the PCR process that all of you have now heard of thanks to our wonderful pandemic these past 2 years. And then you read in the sequence, and we see if we can detect this abnormality in the DNA. It looks something like this. We have a long string of DNA, some of which is cut off by our restriction endonucleases. And then in there, in the purple, you can see, it's a little hard to get with the contrast here, but there is a substitution of an A for a letter G where there should be. And this is the entire cause of hemochromatosis. So if we can read the genetic code and find this pattern and find the change in the pattern, then we can actually save a lot of people's lives. We have a few ways of doing this using our algorithmic techniques that we've found so far. Given a sequence of characters, so this will be our genetic code T, and a pattern, this will be the specific mutation that we're looking for, Your task is to find the index at which this mutation occurs. Where in the genetic code does this change occur, and does it occur? Essentially what you're looking for is for every possible index in the genetic code, does this pattern exist? And the way we check for the pattern is our pattern is of length m in this instance, and we check each of the indices starting at some location to make sure that the entirety of the pattern is present. Otherwise, we return not found. This is our linear search algorithm that we've already seen could be one way to solve this. However, now we have the added extension that we're not just searching for a single item in the array, rather we're searching for a much larger pattern, for a sequence of letters. So rather than, because if we looked for a single A in the genetic code, there are A's everywhere. So obviously our typical linear search through an array won't work. We need to look through this larger pattern and find this sequence such that we can spot this change. Let's build up our solution piece by piece for linear pattern search. We'll start off with a simple algorithm before moving on to probably the most complex algorithm of the semester. But in the meantime, let's go from the simple to the more complex. So our intuition, our very first intuition for solving this problem is that a matching pattern must start at some location in the target string, in the larger string in our genetic code. And let's call the place where it starts k. And the string is going to be of length n. That's an error on my slide. I've switched m and n. So at some point in the lecture, we're going to switch which is m and which is n. Bear with me, I'll point it out to you when it happens. So let's say our genetic code is of length m, and our pattern that we're looking for, our special sequence, our mutation, is of length n. And in order for us to successfully find this pattern within the larger string, it must be true that at each of the indices, starting with k, the target string and the pattern that we're looking for match. That is, if our pattern starts with G, and our target string, once we're found at index K starts with G, then we check the next letter along. If the next letter in our pattern, in our mutation that we're looking for is A, and the next letter in the target string is also A, we keep moving along. This is an example of a match. If we do this for all the possible values in the pattern string that we're looking for, we've successfully found an overall match and have found our mutation and can hopefully save a few lives. Our next intuition is that a pattern of length n, so if our sequence, our mutation sequence that we're looking for is of length n, and if there aren't n letters left in the string, then we should just quit because there aren't enough letters for a possible match to be found, and so we should terminate early. Remember our termination conditions inside our loops? This seems pretty similar to that. Our fourth intuition is that as soon as you find the first non-matching character at an index after k, you can just move on. We know that the pattern can't possibly match if, say, the third index of the mutation sequence and the third index of the place where we've started looking for the pattern in the larger string, if they don't match, then we shouldn't keep looking at all the remaining letters in the mutation. We should just give up at that point and start again at the next letter and see if our pattern's there. But there's one more useful one. If the pattern is of length m and you've checked m characters and you haven't quit early, this is our success condition. You've found the pattern. So this is saying that if we've checked m characters and all the m characters have matched and we haven't ended early like in our previous intuition, then we're done. We found the pattern. Let's convert this into an actual algorithm. Here is the very broadly written in nice English pseudocode version, and we'll go one step at a time, going from this version to a version that looks a little more like C code, and then finally to C code itself. Let's test each possible index in the string S for a match. After all, any of those places could be where our mutation begins. In order to test for a match, check if the current place that we're looking for in the string and the pattern match. If they don't, well, that's our early termination condition, stop. If you've stopped and you're at the very end of the pattern, you've matched the whole thing, and then all we do is we loop this over and over and over, incrementing the current index with each time. How many possible indices are there for how many different places possible in the original string are there for the pattern to begin? Well, if the string is of length n, there are roughly n possible indices, or this is the point at which the slides have switched. N is now the length of the overall genetic code, and m is the length of the pattern. I'll fix that up on the slides for you for when I upload them at the end of the week. So, resetting, n is the length of our overall genetic code now, and there are n possible places as a result where our pattern could begin, where our mutation could begin. But some of you are smarter. You'll say, well, we actually, remember our intuition, I think it was number 3? We can't start the pattern all the way at the very, very end of the string because there aren't enough letters left. So you're right, technically this is n minus m possible places to account for the fact that we have to have at least enough letters left for the mutation to be found. Once we have picked a potential location for the mutation to begin, then there are m letters in the mutation check that we're doing. And so for each of those n locations, we have to do m checks. We have to check m letters. So to test for a match for each index of the pattern, check if the current index of the string and the pattern match, and if they don't, stop and move on to the next possible location for a match. So this gives us a big O of NM algorithm, because for each possible location, we have to do m amount of work, in the worst case, to check if we're matched. This is the more formalized pseudocode version of what we were just talking about, and it's not too complicated. We'll do it with a demo on the iPad in just a moment. Beautiful. Here is a sample version of linear pattern search that we're going to run through with our beautiful pseudocode on the side here. And our sample string over here, this is going to be equivalent to to someone's full DNA, and then the mutation that we're looking for is our pattern. So start S at 0. I think maybe these should be swapped. Ooh. Give me a second to ungroup these items. Ungroup. The KMP uses C.
Oh, it's just the pseudocode.
Yeah. So C is going to be equivalent to our variable I in our pseudocode there. We'll fix it up for next time. Okay, so we start at the very beginning where S is going to be, is there a match, starting at this location in the genetic code. While S is less than n minus m, where n is the length of our overall string, so that would be 8, and our pattern is of length 3, so m is 3. So while we still have room for the pattern, so while there is still enough letters left for us to check, keep going along. Okay, for I is 0 to, or for C is 0 to m minus 1, because m is 3, that'll take us to this location underneath the F. Check each letter against the letter in S. If S plus I, or C, does not equal P of I, our pattern, we'll annotate this better, that'll be our pattern, and that'll be our string, and this will be our pattern. If they don't match, break and increment S. And increment S. Big S. If they do match, keep moving them along. So let's try this out. Make that a little smaller again. Do A and D match? No. So we're at our condition here. They don't match, break out of that for loop, and move S along 1. So we'll move S along 1, and that means moving our pattern to check to the next location. Do B and D match? No. Move S along 1. Do C and D match? No, they don't. Move it along again. Now we've finally got a match between them. So we follow the other branch in our loop. If the two of them match, go along again, and am I missing an increment of... Oh, yeah, the loop condition is there. This is incrementing our I. So for I equals 0 to m minus 1, increment I, check S plus I, and in this case, I is equal to 1. So S plus I is pointing to that. We check if those two are the same. Yes, they are. So we increment I, We move that along. Do they match? They match. And now we're in this condition over here. I is equal to m. So I equal to m. And so we break and we return the index at which we found the pattern, which is S. The pattern starts at location 3 in our larger string. In our genetic code, we've found the mutation, and so we exit, and our algorithm has finished. Now, Liam, microphone. What are some potential problems with this strategy? Why might this not be the best way to go about searching through a very large string? Does anyone have any ideas why this might not be the fastest way we could go about doing things? Okay. D, you're up.
Is it because that they have to iterate through all the variables?
So whatever we do, we're going to have to check every possible place to see if it starts, because we don't know at which of these locations it starts. What about, hold the microphone for a second for me. What would happen if our pattern was ABF? If the thing that we were looking for was ABF. Oh, Liam, was that you? No. Okay, someone on Zoom. If our pattern was ABF, we'd start with 0 and 1, and we'd check the first two letters, and the third letter wouldn't be a problem. So it doesn't seem from this example like we're wasting too much of our energy. Let's try a different example. Hold on to the microphone, and we'll come back to you in a second. Here's another example of a potential pattern that we could look for. Hold on to the mic. And now look what happens if we try our pattern search again. At each of the possible starting locations, we have a lot of possible matches. So we check, is A equal to A? Is A equal to A? Is A equal to A? Is A equal to B? No, they're not. And so we move over by 1. And now, again, we check, is A equal to A? Is A equal to A? Is A equal to A? It's not equal to A, and we move it over by 1. And again, A equal A. What's happening? Are we doing any repeated work here? D, so can you explain to me what the repeated work is? Hold the microphone up to your mouth.
So, every time we have to iterate through all the just exclude all the A's in the pattern, so that it's kind of like a big old n squared work.
So it's not quite n squared because this is of length m. And so each time, for each of the n letters, for each of the n possible locations, we're doing m work. But you're right that there is a multiplication going on. It is n by m, so this is big O of nm. But we're repeating ourselves a number of times here. Do you have an idea of what we might try and do with the pattern? You don't have to come up with the full algorithm, but what could we do to save ourselves some work? Oop. Boxiang, do you want to give it a go? What can we do to save ourselves some effort?
I guess you can create a subarray of like the four elements that you check, and you iterate to the next one, and then you can check the new one with the old one, just like the last element.
So let's walk through that with the iPad so it's a little easier. You're saying that, okay, I have to start at the beginning. There's no way around that. So I check does A equal A, does A equal A, does A equal A, and then I see a mismatch. What should I do with the pattern now?
I guess if you already know that, I guess the second index is the same as the first index of the pattern, then you don't need to check that anymore when you move the...
So you're saying that maybe we should move this along and skip some of the letters because we've already gained some information. Yeah. Why don't you pass the microphone back to Yash, and Yash will give us, I think he had some thoughts on this as well.
Yeah, I think you can skip it ahead to 3. So just because you know that 0, 1, and 2 are all A, and you know that 3 is, isn't 3 yet? 3 is also A, so we just check that A's in the next check, and then like the last A, and then you check the rest.
So Yash's idea is that at some point we've already gained the information about a match between what's at the start of our pattern. So we know we have 3 A's at the start of our pattern, and we know that there are A's all along here. So we should be able to skip a little along, and this will take me a second to do with the way the iPad works, but we should be able to skip some of the letters that we've already seen. Exactly how we do that is going to be the focus of today's class on the KMP algorithm. As we've seen, our linear search algorithm, our linear pattern search algorithm works pretty poorly in some ways. We end up doing all this repeated work to the extent that we get n by m total comparisons in the worst case. On average, you're not even going to match the first character, so this might not turn out to be so bad. Our worst case might not be the average case, which really is the case for English text. English text, most of the time, if you have a pattern that you're looking for in a large body of English text, every time you get to the first character, you're not going to match. But for a genetic code, this is probably not going to be true. Why? Why might it not be true for a genetic code when it's true for English text? What does English have that a genetic code doesn't?
There's no characters in the English alphabet.
Yeah, so in English we've got 26 different possible things to choose from at every location. So the chance that a random, let's say our pattern's random and our string is random, the chance that we'll randomly pick the same 1 in 26 letters for both the start of the pattern and the start of the string is pretty low. And as you go more and more, if we're looking at 3 random letters for a string and 3 random letters for a pattern, that's going to decrease by powers of 26. So with English text, our linear pattern search might not be so bad, but for the genetic code, we definitely need something more efficient. And this is really one of the big motivating factors behind our use of KMP. Now, I have dropped my clicker somewhere. This always happens. Okay, we'll find it again at some point. Liam will survey. So we need a new tool in order to develop this. There it is, underneath the iPad. We're going to need a new tool in order to develop our understanding of this skipping behavior. And this has not been part of courses prior and is not in the textbook, so if you're having issues with it, we'll put some links up on the LMS for you to access, and as well, as always, the recordings of this lecture will be available. This is a tool from computer science theory known as finite state automata. What a finite state automata is it's an abstraction over a particular type of machine. It's another way of representing different forms of algorithms that's a little more limited to the general class of algorithms that we can program using a very complex language like C. The way it works is we have a mix of states and transitions. You can think of a state as a certain mode that a machine is in. So for example, a traffic light has 3 different modes. It has red mode, amber mode, and green mode. So those would be our different states. A transition is the allowed ways that you can change between them. So you can go from green to amber, and you can go from amber to red, but you can't go from green to red directly without amber. There is no allowable transition in the traffic lights that allows for this particular transition. The other element that some state machines have is an accept state. So this is when your job is complete. Now, traffic lights obviously don't have an accept state. There's no more right color of a traffic light than other, but you could imagine if you're developing an algorithm that works around these principles, you could have a bunch of different modes that it will be in, and one of the modes could be your success modes. Let's look at this concretely in terms of a familiar ordinary object. Take a look at this master padlock. Here, the code is 421731. Our goal is to unlock the padlock. This will be our accept or our success state. That's unlocked at the top, and we denote it with 2 rings around it. Our lock state will typically be our starting state, but in this case, it doesn't really matter where you begin. This process works regardless. In order to get from the lock state to the unlock state, we need to make 3 different transitions. That is, entering each of the combinations in turn. If at any point, even no matter how many of the numbers you've entered correctly, if the next number you enter is incorrect, you go back to that locked position in the very first place. And so that's denoted here by the arrows going from both states A and B, which are are intermediate states that take us back to the locked position. You can also see from the locked position, if you enter a number that isn't 42, which is the first correct number in the sequence, you stay in the locked position. So this is another form of transition that allows you to go from a state to the same state, showing that you haven't made progress on a certain input. And that's another feature of these state diagrams, is you can think of each of these transitions as corresponding to certain inputs to our machine. So in this case, the winning input to our machine is 42, 17, 31. If we entered 42 and then 17, that would take us to state B. And then if we entered anything other than 17 at that point, that takes us back to lock. And you can play this game with yourself if you really need a way to get distracted during holidays. Draw up a state machine for some familiar object and familiarize yourself with the transitions. Now, we can also tabulate these transitions in a different form. We don't just have to use this diagram with arrows and circles. We can write it out in a table like this that says what the current state is, what the next state is, and how you go between them. So if we want to get from locked to A, the way we can do it is by entering 42 in locked. If we enter not 42 at the locked position, that'll take us to the locked position again. So for any finite state automata, you can build up a matrix or an array, given one of our tools in C, to indicate the possible allowed transitions. We can also reorder this table. It doesn't really matter what order you list the transition in. They're the same transitions either way. So now you'll see that I have ordered it in a particular way such that all the transitions that take you back to locked are on one side, and then all the rest of the transitions are the other. This allows us to write some simple pseudocode, noting that in the majority of cases, if we have something that doesn't match the next entry in the code, we just go back to the first thing. So here's some pseudocode that implements a simplified version of this state machine. Instead of having all the transitions, we actually only have the set of transitions that allow us to make progress, because we already know in our minds that all of the other transitions reset us to the beginning. This is some simple C code that says, while you haven't reached the end of our set of transitions and you're still receiving input, check if the current input is equal to the step of the sequence of transitions that you're up to. If it doesn't match, go back to the start, you're back in the locked position, otherwise get the next input. And this finishes as soon as I gets to 3, which would indicate that we have gone all the way to the end of our possible allowable states. We don't have time to step through this in an actual C code, but if you want to have a go playing with this and drawing out what happens in comparison to a diagram on the side, that's another activity that would help familiarize you with these state diagrams. Now we're ready with our new fancy computer science theory tool to revisit our pattern search problem. We have our linear pattern search, whose state diagram is actually kind of boring. If you enter, let's say our pattern is our AAAB. If you match the next letter that you have to match, so if your input is another A, except at the very end, move to the next possible state. If your letter is anything other than A, well, then it's not a match, and for linear pattern search, our algorithm that repeats a lot of the work, we go back all the way to the start. There are also some other things that we do alongside this to make it work in the context of a broader program. We are going to backtrack our variables S and C that we did on the iPad. If you remember, we had our variables S and C over here. And we know that for linear pattern search, every time that we detect a mismatch, we have to move C all the way back over, and we move S over one space. And so that's where our repeated work comes from in this instance, is in this state diagram, the fact that for all our states, we go back all the way to the start again. Now, Yasha's and Boxiang's suggestion was that maybe we can construct a different state diagram. Maybe we have some places where we don't have to go all the way back to the beginning and can instead actually skip some of the work. Here is a short animation or a short video of linear pattern search. And you can see what's happening a lot faster than I was able to do on the iPad. At each time, we are doing all this repeated work, checking all those A's over and over and over and over. It is slow. I could have sped that up even to 800 times and we would still be sitting here a while. Let's just move on. This is a slightly different pattern that we're searching for, and you'll notice the state diagram is again the same. We're not taking advantage of any special features of the pattern. So last time we could have taken advantage of the fact that there were lots of A's in the pattern, and so that allows us to skip some number of A's. In this pattern as well, it has a different structure. It's not all A's, but there might still be some optimizations that we could make to this state diagram. We're going to look over the next lecture and the rest of today at these two different patterns and see how their structure contributes to creating specialized finite state automata for each of them that allow us to make much faster searches and save on some of the work. So here is linear pattern search on our other string. You can see it's not quite as bad. It's not the worst case, but we're still doing some repeated work. And then we finally have our match. The holy grail of what we've been looking for this whole class so far is to find a way to cut out this multiplicative M factor, the need to go through all the pattern every time in the average case. Well, this is the Knuth-Morris-Pratt algorithm that solves this problem for us and allows us to achieve this in O of n time. The intuition here is that for a given location S in the target and for a location I in the pattern, so we're just setting up our variables, if there is a mismatch between the pattern and the target, skip I letters in the target where I is the number of letters we are into the pattern. So like Yash was saying, if we're 5 letters into the pattern and we've seen 5 A's, maybe we can skip 5 A's. But there was an exception to this that is clearer in this example. Because our pattern doesn't have the same letter over and over and over again, notice that the E is repeated. So when we check the first E, when we check the second E in the pattern with the second E in the target string, we're not actually sure if the E in the target string, our E in the biggest string, is the first E in the pattern or the second E in the pattern. So we're going to need to make some adjustments for when our pattern has repetitions of itself in it. So if the pattern begins to repeat itself in those I letters, we're going to need to skip only until we can align the next possible place that the pattern has started. So we can't just skip all the letters that we've seen. If there's some repetition inside our pattern, we're going to need to reduce the amount that we skip. And we'll look at how to compute these values momentarily. This is an animation of how the KMP algorithm would work. And then we'll go and break it down step by step. It might actually take us till partway through next lecture to fully unpack it, but this should at least give you a first glance at this skipping process. Let's give it a run. So you can see now we are skipping many of the comparisons of our pattern string over and over. We're not checking all those 4 A's, we're only checking that last letter. Doesn't match, doesn't match, doesn't match. And overall, we have now done O of n comparisons instead of O n m comparisons. This is what our new state diagram looks like. And don't worry, we will go over slowly with how to construct one of these. I also have an alternate version of this that's actually, I think, not much easier to read given the contrast of the lecture theatre we're in, but you can see that we have some of the arrows take us back all the way to the start. So there are going to be some instances in which we have no choice but to begin all over again, but there are other instances in which we are able to jump partway back. And this is going to be how we will run our KMP algorithm. So like with our other state diagram for our finite state automata with the lock, our goal here is to construct a table in our C code that matches the finite state automata. The way this is going to work is for each of the red arrows, we're going to construct an array that specifies where those arrows land. So if the arrow lands at the 0th element, we're going to put in a 0. If the arrow lands at a 1, then we're going to put in a 1. As an example, look at state E2 over there. State E2 jumps over to E1, and E1 is at index 1. So to encode that arrow in our transition table, we're going to put a 1 in our matrix there, in our array. You'll also notice that there is one element in this that doesn't make sense. That's our -1 over in the corner underneath the start. We're going to use that to enable our program to detect when we actually have to do a full reset. You can operate without it, but it'll make our code a little neater, so don't worry about that too much. And in every other instance, the arrow that goes back, it's for an arrow that goes from element Y to element Z. We encode that by writing in the yth position the number Z. So another example would be state E5 goes all the way back to state E2. And let's count 0, 1, 2, 3. That means under E5 in our array, when we construct it, we're going to write the number 3, which corresponds to that index. Once we have this, our algorithm is actually going to be not too complicated. If we have a match, keep going along. And if we don't have a match, use this table to figure out where to skip, both where to start the pattern again and where to shift the pattern along to, and to account for this discrepancy if the pattern has repeated itself. We're now going to actually do this much more slowly and figure out how this is going to work overall. Now, this is the moment you've been waiting for, a very slow and methodical work through of the KMP algorithm. Now, again, this part is quite difficult. If I get it wrong, please have some grace, and if you get it wrong, have grace for yourselves too, but we will go as slowly as necessary to get it right. One thing to note here is in our pattern, let's take a pattern that has a little bit of repetition. Our repetition here is ABC, and ABC repeats. So if we find ABC in the target string, we won't know which of the ABCs we're aligned to. Now, assuming we're starting at the beginning, if we see, for example, in our target string A, B, C, D, A, B, Q, and we've looked at this A and this B, we haven't looked at this Q yet, so don't worry about it. But this AB over here could either have been this AB over here, the one at the end of the target string, could either be this AB in the pattern, or it could be this AB in the pattern. We're not sure whether the AB in the target string is an AB that begins there or there. Now, if we made our pattern longer, and if we did let me add one more letter there. Now if we move our pattern along and we come across this ABC over here, we're now not sure, or this AB over here, we're now not sure if it's this AB or that AB. So our goal in constructing our state transition diagram should be to find all the places where the string is repeating itself as a prefix. So we care about this bit at the beginning of the pattern because it's only the beginning of the pattern where we could start again. If we just find a random D hanging around, we're not worried. Let's pick another D. Write that on. If we just see a D hanging out on its own in the target string, we don't need to worry about the fact that it appears somewhere in the pattern. Why? Because in order for the D in the pattern to match, everything before it must already have matched. So we're actually looking for prefixes that match suffixes. So if we write out our list of all prefixes in our original string, our prefixes are A, then AB, then ABC, then ABCD, then ABCDA, and then so on and so forth. Our suffixes would be, I think I've screwed this up now by adding random letters on. Oh, I know what the issue is. These prefixes, they're pattern prefixes, not prefixes of the target string. Yes. So A, and then AB, then ABC, then ABCD, and so on and so forth. Now let's look at all the different suffixes. We have a suffix C, we have a suffix BC, we have a suffix ABC, then DABC, and so on and so forth. And our goal is to find the places where these two lists are the same. So for example, we see that ABC and ABC are both the same here, and we're looking for the longest one that matches because this tells us how far we'll have to go back. In this case, 0, 1, and 2 matches our suffix over here, and that is the longest we can go because if we try the suffix DABC, there's no prefix DABC that matches. The longest prefix that we've got that matches a suffix is ABC. This allows us to start building up our state diagram. There we go. Our goal here is to figure out how far we can go back before running into the same pattern again. So assuming that we've done this task of figuring out where the longest prefixes are and how long they are, this allows us to build up our failure function. Here I've already computed for you the table that goes along with our state diagram. And let's look at this in a little more detail. We have a pattern over here. This is a pattern, not a target string, very important. And we're looking for these repeated suffixes and prefixes in the longest prefix that matches a suffix in our pattern string. So in this case, let's look at E. Does E reoccur as E is a prefix? Does it reoccur anywhere in our string? Yeah, it reoccurs over here. And in that instance, there's no longer we can't extend this out longer because this goes EL and that goes EM. So the furthest amount of work we can save is by going from this E over here, E2, to E1. So what we do, we draw an arrow from E2 to E1, and that's our arrow here. Again, this is because this prefix starts EL, and this one starts EM. So if we've seen EM, we can't go back already to the point of being at the L. The furthest we can go, the most work we can save is by going back to that first E. And remember, the further along this direction we go, the more work we've saved. So what we do as a result is in our transition table, we write a number 1 because that is the place that we can go back to. If we see EL, and then we stop matching, if we've seen EL and then M, we have to go back all the way to the beginning. Why? Well, we can't save any work because there's no repetition in our pattern here to enable us to latch onto. We'd have to start again because we haven't seen another E, and in order to save work, we have to have something that's being repeated. Let's keep going along. If we've seen EL, E, M, and now we see another E again. Well, this time, this E could go back to... Can this E go back to here? No, it can't, because we would have to have seen EL already in our suffix, but we haven't. The furthest we can save ourselves is by going all the way back to E1 again at this point. Well, let me make that arrow a little better. Furthest we can go back is to E1 again, and so you'll see that there is an arrow from E3 going to E1, and we note that down. Now we finally get to a suffix that's a little longer, and that'll match a longer prefix as well. So if we've just seen EL, it can either be because we're already at this point in our pattern, but we didn't match just now. So we know that we shouldn't continue going along in this direction, because in order to keep going along this direction, we need to see another E. But perhaps we can jump back to this point in our machine and be on the mode L1. Why can we do this? We've just seen an E, we've just seen an L, and this allows us to jump back to another position in our machine where we also have just seen an E and just seen an L, but we can't jump back anywhere. It has to be to a prefix, It has to be a set of letters starting at the start that matches that, because we have to have had a way to get there in the first place. For example, if there was an E and an L there, we wouldn't be able to jump to that one because we wouldn't have seen that other E and the L prior. You can only jump back if you've got a way to get all the way from the letters you've just seen, in this case an E and an L, all along the beginning path again. So we've just seen E and L. That allows us to jump back to the earlier E and L because that's another possible place in our machine that we could have gotten to. Now, what if we're at this point in the pattern? We have gone E, L, E, M, E, L, E. We have E, L, E. And if we look at the start of our machine again, there is a possible path starting at the beginning that goes E, L, E. And so, if we don't match the next letter over here, if we're not matching that L, we can instead go back and draw an arrow. And this is our green arrow here. We can go back and jump the machine all the way back to ELE mode, because that's valid, because the last three letters we saw were ELE, and ELE is a prefix as well. Let's try extending this one further and see what happens. We're now at ELEL. This doesn't work anymore. The furthest we can go back is to rescue this ELE bit that we've seen. And it's still valid for us to go to that ELE over here. We just can't go one further because that next letter is not an L. If that were an L there, we could go one further. But because it isn't, we still have this suffix over here that still matches ELE. We have still just seen ELE, so we can go back from the start of our machine again to ELE. Now, the last one, why is this 3? Well, the last three letters that we just saw were ELE, and so despite the fact that previously when we had just gotten up to that point over here, we could do a little less work, because we've seen ELE again, this gives us positions that we can go to. And I think, yeah, so we draw our arrow back over here, because we can again match ELE. Now we will save it for next time, the other two layers of the transition matrix. But you might ask, why don't we have any entries for our forward links over here? Well, as clever coders, we know that because all of these links just point to I+1, say if we're at E1, it points, which is at index 1, that link just points to 2. And if we're at 2, it just points to 3. So we don't actually bother encoding that inside our C program for KMP, or even bother writing out another array for it, because that's implicit in the structure of our problem. We know that our problem involves this transition from only if we're correct, it involves transitioning to the next one along, and so we can just implicitly have that within our code. And I think that is enough on the complexity of KMP for today. We will finish off with how we put this all together and do our skipping tomorrow. Thank you very much, and I will see you tomorrow for our last lecture before the mid-semester break. Catch you all soon.